Okay, in this problem we have a toy rocket being shot straight up in the air with an initial velocity, and it's going to travel a specific vertical distance before falling back down to Earth. We'll start this problem with a motion diagram. So, we know that it starts from a position, we'll say it's near the ground, and we'll call that position 0, and it's going to have a fairly substantial velocity at the beginning. This problem doesn't say anything about acceleration, but given the specifics of the problem, it's safe to assume that this is a free fall problem, which means that my acceleration will be pointing downwards. So what that means is that when this rocket is moving upwards, the velocities that I'm drawing here should be getting shorter each time. And we can go through and label a bunch of these. So this one will be 1, this can be 2, that can be 3. And eventually I'll get to a point up top, which is what we call the turning point. I'm going to label that position 4. And at this point, the velocity is going to be 0. Now, this particular problem explicitly says that it only travels vertically. But in doing these motion diagrams, when you have motion in one dimension, but that happens to move back and forth, it can be difficult to draw that. So we're going to purposely offset it, even though it doesn't say anything about the toy rocket moving horizontally. So again, this is my turning point. And after that point, it's going to fall downwards until it reaches the bottom. And we can label each of these as well. So for both sides of this, when it's going up and when it's going down, the acceleration is the same, and it is pointed downwards. So the last thing that I need to do is I need to pick a position, a direction for it to be positive or negative. And I generally pick up as being positive. So we'll go through and work all of our measurements based on that. So next we need to focus on our knowns. So given the problem, I know that the change in distance from when it is at its highest point to when it falls back down, and I'm going to label that as 8 and then 4. So basically we're talking about this distance here. Is 27 meters. Now you don't have to use my notation. For me, it makes sense to me because I like to be exact. Maybe I'm working a problem later or another part of this and it wants me to look at a different range of positions for between two different points, and so this way I don't have to worry about messing any of that up. It's a way for me purposely to be consistent with myself. You just need to find what works for you. All right, so I have that distance, and in fact that should be a negative distance because it is pointing downward, or it's traveling downwards. It's falling that distance down. But we can also notice that the same distance it travels upwards. So I'm going to actually mark both of them down, and that would be a positive distance. So that means when it goes up here, it's traveling one distance, and it travels the same coming down. And so we're going to mark them as positive and negative. So when it's traveling upwards, it's traveling a positive distance, and when it's falling back down, it's traveling a negative distance, and that's solely because of how we picked our positive direction. Now, it also gives me an initial velocity of 23 meters per second. We've already said that our acceleration, it's free fall. So that means because I picked upwards to be positive, this is going to be negative g. And you can remember that that is negative 9.8 meters per second squared. And lastly, I know that my velocity at that turning point is going to be 0. That's the definition of the turning point, is the point in the trajectory when the velocity is 0. That's when it changes directions. And then my unknown for this problem, the thing the problem is asking me to do, is how long was the rocket in the air? So that's the total elapsed time for the object, which we'll mark as 80 here. Although now that I'm looking at it, they should be more like 9s, but I think you get the idea at this point. We'll continue with my same notation. So in order to go through and solve this problem, which is part B, there are actually a couple different paths that you can go through and do, and I'm going to model both of them so you can see which one works best for you. So again, you would never have to go through and do both of these. But I want you to go through and see what they look like. So one of them, let's call this Roman numeral 1, uses our knowledge that we know based on the problem that the launch and landing position are the same, occur essentially at the same Y position. And that's what I already used to show you when I drew the motion diagram and the picture. I already utilized this information. In fact, we explicitly wrote down that those distances traveled are the same. So if the distances traveled are the same and the accelerations are the same, then that's telling me something about the time as well. So I can essentially say that the amount of time it took the object to get to that turning point, if I multiply that by 2, that's going to be its total travel time, which again is the thing that I want to go through and find out, which means that I can go through and solve the simpler problem of just solving it either going just up or either coming just down, and then just multiply that time by 2. So that's what we're going to go through and do for our first possible path. So given the knowns and unknowns that I have, I'm going to go through and utilize and focus just on the moving upwards. So I'm going to use the kinematic equation that looks something like the final velocity is equal to the initial velocity plus the acceleration times the elapsed time. So if I change the notation for the problem that we're looking at here, so this would be the velocity at position 4 is equal to the velocity at position 0 plus the acceleration times the elapsed time for sub 40, basically meaning from launch till it hits that turning point. Now I know that the velocity at the turning point is 0, so I can go through and do that, do a little algebra. I move my initial velocity over to the left-hand side. I can plug in that I know my acceleration is equal to negative g. So now you can see that I have negative signs on both sides, which means that I can basically just get rid of them and ignore them, multiply everything by -1, and now solve it for that time. Plugging in my numbers, that velocity was 23 meters per second, and g is 9.80 meters per second squared. Plug that into your calculator, you should get 2.96 seconds. And then if I multiply that by 2 to get my final answer, since what I've done so far is only find half the time, I will find the total elapsed time is then 5.9 seconds. Okay, so that is possible path 1. Possible path 2 is actually going to utilize everything we have here. So it's going to say that the starting position and the ending position are actually the same y position. So I'm going to use a slightly different kinematic equation, And it's going to be the one that involves the final position is equal to the initial position plus the initial velocity times the elapsed time plus 1/2 the acceleration times the elapsed time squared. But I'm going to use this for the entire path. Which means that my final position is going to be equal to my initial position, which is also going to be equal to 0. Because they started and ended at exactly the same y position. So it went up and went back down, but it landed at the same y position that it started with. So that means I have 0 equals 0, and now I'll go through and plug in some of these velocities. So this is the velocity at its initial position. This is the full elapsed time that I want to try and find. 1/2, I'm going to go ahead and leave it as a for right now, but we'll plug it in as -g in just a moment. First, we're going to be able to go through and do a little bit of algebra. So I'm going to move this to the other side of the equality, and that will turn it negative. And now I'm going to plug in the -g for the acceleration. So at this point, you should be able to see that I have a negative on both sides. And I also have a delta t on both sides, which means I can get rid of one of those as well. So if I rewrite this, I get that initial velocity is now equal to 1/2 g delta t sub 80. And now I have only a little bit of algebra left to go through and solve this. And if you look at this, this is 2 times velocity over g, which is exactly the ratio we had up here in our initial first one, which means when you go through and plug those numbers in, you'll find that the answer is, again, 5.9 seconds. So in thinking about these two different possible paths that we took, the first one required us to know that they launched and landed at the same y position. And so that meant that the trajectory was symmetric, and so that it was going to take the same amount of time to go up as it was to come down. Now, if you happen to have something that does not launch at the same y position as it lands, then you cannot use possible path 1. You have to use possible path 2, and it means your y final and your y initial will be different. So possible path 2 will always work regardless of what your starting and ending positions are. Possible path 1 will only work when they happen to be symmetric. So that's something to keep in mind when you're working these problems.